I'm going to go over question number 7 from the 2019 AP Chemistry exam. A student dissolved a 0.139 gram sample of oxalic acid in water in an Erlenmeyer flask. Then the student titrated the oxalic acid solution with a solution of potassium permanganate, which has a dark purple color. The balanced chemical equation for the reaction that occurred during the titration is shown above. Now the potassium is a spectator ion, so it was canceled out. Identify the species that was reduced in the titration reaction. Justify your answer in terms of oxidation numbers. So what we're going to want to do here is to look at this reaction a little more closely. And so I've kind of moved it here. Now, each of these, each of the chemicals in here, each of the species has an oxidation number, and it looks a little daunting, but it's really not a bad situation. So we're going to go back and say, well, in a compound, hydrogen is almost always +1. So there's a hydrogen, there's a hydrogen, there's a hydrogen. So these are all these compounds. Hydrogen is +1, so it is not being oxidized or reduced. So that's not the chemical we want. Oxygen in its compounds is almost always -2. And the time that it's not -2 is when it's in peroxide, and there's no peroxide here. So oxygen is not the chemical we're looking for. So the ones we really are looking for, either it's going to be manganese or it's going to be carbon. So let's start with manganese. Now manganese, a little bit easy. Over here on the right, here's the manganese ion. If we have something that's an ion, then its oxidation state is the same as the ion. So it's +2, a manganese 2+ ion has an oxidation state of +2. Over here, permanganate, a little bit more complicated, but not bad. So I'm going to rewrite it. And we can kind of do this as a algebra problem. So let's say the number for manganese is X, and we know that we have 4 minus 2's, and altogether it's going to end up being -1. So X plus 4 minus 2's equals -1, so this would be -8. So this must be +7. So +7 minus 8 gives us -1. So manganese in permanganate, that species is reduced because it goes from a +7 state to a +2 state. And if we say that much, we just earn 1 point. Now the student used a 50 milliliter burette to add the permanganate to the oxalic acid until a faint lavender color was observed in the flask. Now again, this faint lavender color is leftover permanganate, an indication that the endpoint of the titration has been reached. The initial and final volume readings of the solution in the burette are shown below. Write down the initial reading and the final reading, and then use them to determine the volume of permanganate that was added during the titration. So let's look at this kind of closely. Now, burettes are a little bit odd because the numbers get larger as you go down, and unlike a graduated cylinder where it starts at 0 at the bottom and gets larger as you go up, a graduated cylinder, you were trying to measure how much liquid you put into that cylinder. That's why the numbers go up, because the more you add, the more you have. But a burette, you're interested in how much liquid has been removed. So at the top of the burette, like say 0, then that means you've removed 0 liquid. And as you go down, 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 you remove more. So it's an upside down scale. So we look at this. Here's 3 and here's 4. So we know our answer, our first reading, is somewhere greater than 3. And we can see that if we look at our lines, it's 3.1, 3.2, 3.3, 3.4. So it's 3.3 something. And now we're going to have to estimate. And to me, the bottom of the meniscus looks like it's a little bit more than halfway. I'm going to say it's 3.37. These are milliliters. So because there are lines for the 10th place, I have to read that to the 100th place. Now, in the same way, on the final numbers, I can see it's between 29 and 30. Okay, in fact, so it says 29, and I know it's between 5.5 and 0.6, so I can say 29.5. And again, I think it looks like it's about the same place. So 29.57 milliliters. So if we want to get a volume, then it's always final minus initial. So I have 29.57 minus 3.37. So, oh boy, 3 from 15 would be 2. And this is going to be the 6. And run out. So it looks like we have 6.20 is the, I'm sorry, 26.20 is the volume of the titrant that I've used. Now, if I get to that point here, that is worth 1 point. Now, given the concentration of the permanganate was 0.235 molar, calculate the number of moles of the permanganate ions that completely reacted with the oxalic acid. So we have our number up here, 26.20, so we're going to start with that. And molarity, I'm going to use that as a conversion factor, but that's moles per liter, so I need to change my milliliters into liters, so I know that in 1 liter there's 1,000 milliliters. And then doing my 0.235 moles per liter, so 1 liter is 0.0235 moles, and that's moles of KMnO4, which would also be moles of MnO4 minus, and that comes out to be 0.000616 moles. I'm going to write that again, 0.000616 moles. Now, significant figures. Okay, this number here has 3 significant figures. Okay, this one, here's 4 significant figures and 3 significant figures, but since we subtracted those 2, we actually do end up with 4 significant figures. But our answer is only going to have 3 significant figures. So this number would be the correct answer, and that is worth 1 point. Now, that's 3 points so far. The student proposes to perform another titration using a 0.39 gram sample of oxalic acid. That's the same as before, but this time using 0.00143 molar KMnO4. Now before, they used a 0.0235 molar KMnO4. Would this titrant concentration be a reasonable choice to use if the student followed the same procedure and used the same equipment as before? Okay, justify your response. Now the answer for this is no. Okay, this would not be reasonable. And the reason is that this is quite a bit more dilute than our original solution. And I calculated that it's like 16.4 times more dilute. In other words, I would need to have about 16 times more of my solution. And before I used 26 milliliters. So that is so dilute, I would have to refill my burette over and over and over and over. And each time I did that, I would lose accuracy or lose precision on my measurements. So no, okay, because the solution is very dilute. And we would need to refill the burette many times. So if we make some kind of observation about the fact that no, this is very dilute, chemically it would work, but it would just not be a practical thing to do. So that's worth another point. That is the 4-point problem, number 7.